intro about how we use radiation in astronomy and astrophysics. So this is what we can say modern day 21st century astronomy looks like. So this is the entire EM spectrum which we are able to study these days, and we have deployed several telescopes and ground observatories which peer into the night skies, obtaining relevant information in several bands of the EM spectrum all day long. For example, if we speak of the radio region in the EM spectrum, we have got several ground observatories. A very good example of that is the GMRT, which is located in Pune. Then coming to infrared, we have got a very famous James Webb Space Telescope. So it is calibrated to receive information in the infrared region of EM spectrum. Then for the visible range, we have got the Hubble Space Telescope. And coming to the UV region, we have got AstroSat 1 and 2, which were launched by ISRO. Then X-ray. So the Chandra X-ray Observatory, which was launched by NASA. That's a very good example of a telescope which observes in the X-ray region of the EM spectrum. And then for gamma rays, we have got several satellites like Fermi and Batsy, which are able to look into the sky and receive light specifically in the gamma region of the EM spectrum. And these are very famously used to detect gamma ray bursts. So gamma ray bursts are actually one of the brightest explosions in the universe, second to Big Bang. And this is something which we have discovered with the help of these satellite or telescopes. Okay, so this was what present astronomy looks like. Now, moving ahead throughout this session and the upcoming sessions, which would be a part of the learner space, we would be coming across several terms related to astronomy. And these are those terms. So the first one is luminosity. So in very simple terms, luminosity is actually the rate at which any given celestial object or star is emitting energy. So it is fundamentally energy emitted per unit time, hence it has got the units of power, which is watt. Next is flux. So flux is the energy which we are receiving per unit time, per unit area. So let's say if we have got a star with luminosity L and it is radiating energy in all directions, so we can imagine a spherical surface at say at some distance r, and let's say we were to find flux at that distance. So the flux would be the luminosity divided by the surface area of this sphere, which is 4 pi r square. So the flux would be L over 4 pi r square. Now, next is spectral flux density. So the flux which we are receiving is actually across the entire EM spectrum. And if we are to analyze some particular region of that, we would be willing to analyze that flux per unit frequency. So hence this has got the units of watt per meter square per hertz. And at last we have got spectral intensity. So again, spectral intensity is just this flux density which is observed per unit solid angle. And it is this quantity which we are using to determine the brightness of the surface of any source which we are observing in the sky. So now that we are pretty much done with all the fundamentals and the basics of radiation and astrophysics, let us jump into the hyperdrive. And the first topic which we come across is black body. So what is a black body? Um, First of all, it's a theoretical object. No perfect object has been found which can perfectly replicate a black body. So it's an idealized physical body which is theoretically said to absorb all the EM radiation which it is receiving, be it of any frequency or at any certain angle of incidence. At the same time, it is also considered to be a perfect emitter, which means that it can emit radiation of all frequencies and all wavelengths, of course, with varying intensities. And the radiation which this black body emits when it is in an equilibrium state with its surrounding, that particular radiation is termed as black body radiation. Okay, so that was what a black body is, but now you may be asking, why should we even care about a black body? We are studying radiation in astrophysics, not theoretical physics. So, a shorter answer to this is, because you took this course and it's a part of this module, you are supposed to study black body. But a better and a longer answer would be that stars are a very good approximation of black body emitters. So if we are able to predict a model for these black bodies and understand their behavior and patterns, we would be very much good in understanding and describing the behavior of stars. So, why do black bodies even produce radiation in the first place? What is the science behind that? So, fundamentally speaking, and starting from the very basics, we all know that electrons in an atom, they are present in certain regions of space termed orbitals around the nucleus. And whenever an electron changes its orbital, it changes its energies. So when an electron from a higher state or a higher orbital jumps to a lower orbital, it releases the excess energy in the form of photon, which we also term as light or radiation. So what role does heat play over here? Now, the role which heat plays over here is that in a body, like let's say for example a black body, the atoms and the molecules, they are present in lattices. So when we heat a certain body, it increases the vibrational energy of those molecules. And when these molecules start vibrating, they start rubbing against each other. And by doing so, they transfer some part of their energy to each other. And this energy, when gets transmitted to the electron, causes the electron to jump to higher orbitals. So the more heat you give, the more temperature would be. The more heat you give, higher would the electrons be able to jump to orbitals. And if they are able to jump to higher orbitals, when they come down to the ground state, they would be emitting much more energy. So if you are able to see in this animation over here, when we are heating, let's say just one molecule, this is vibrating and then transmitting its energy to other molecules in the body. So this is somewhat an idea about how a black body produces radiation. But again, scientists wanted to predict and to find a model using which they can completely understand the black body and theorize its behavior. And in the course of that, there were several attempts to describe a black body. There were several laws which came in the way. And the first one, which was brought into the picture, was the Stefan-Boltzmann law. So Joseph Stefan and Ludwig Boltzmann, they were two people who discovered that the flux which we are receiving from an object is directly proportional to the fold power of its temperature. So if you look at this relation, if you take A on the LHS, so L by A would actually become flux which we are receiving. And to replace that proportionality, they introduced two constants. Sorry, this E is rather a variable, and they introduced this constant called the Stefan-Boltzmann constant. So what is E? E is a term known as emissivity, and emissivity is defined as the ratio which compares the energy which that particular body is presently releasing compared to the energy which it would have emitted had it been a black body. So this E lies in between 0 and 1, and it is exactly equal to 1 when we are speaking of black bodies. Hence, this is what Stephen Boltzmann came up with. Now, next came into the picture Wien. So what Wien did, that he combined the wavelength which is emitted from a black body with the energy distribution among atoms. So he used somewhat a thermodynamic model to describe a black body, and he obtained with this relation. Here V lambda is the spectral radiance for any given wavelength. And you can see this is what he came up with. So the good thing was that for lower wavelengths, it matched pretty much well with the experimental data. However, when we moved on to higher and longer wavelengths, it started diverging from what we were expecting or from what we had calculated experimentally. So again, this was partially correct and not the complete explanation to the black body problem. So to deal with this came the classical approach to this problem. Now, what does the classical approach say? So, according to the classical approach, when we irradiate a black body with some radiation, the cavity within it starts emitting EM waves. And when these EM waves they reflect and interfere with each other within the cavity, they form standing waves. And these waves were then later on treated as harmonic oscillators. And so, if you are able to look at this, these red dots which you can see over here, these are actually the nodes of the standing waves, and these maximum amplitude region are the antinodes. So it was found that the number of nodes or the vibrational modes were actually proportional to the cube of the frequency with which these particles were oscillating, or these waves were oscillating rather. And this led to the Rayleigh-Jeans law. So Rayleigh-Jeans law stated that the spectral radiance for some particular wavelength is actually inversely proportional to the fourth power of wavelength. So according to this, as the wavelength decreases, the amount of intensity with which it is being emitted should increase. And it came from this equipartition theorem only. Uh, Over here, as I said, that the standing waves were treated as harmonic oscillators using the partition theorem proposed by Boltzmann. We could allocate each of those oscillators an average kinetic energy of kVt, where kV is the Boltzmann constant. And by doing so, we got this curve over here. However, there was again one issue with this, that uh, unlike the Wien's approximation, which matched pretty well with shorter wavelengths, the Rayleigh-Jeans law it matched pretty well with longer wavelengths. But as soon as the wavelength started decreasing, and which can also be inferred from over here, that as lambda starts coming closer to zero, b lambda would start increasing, and it would keep increasing up till infinity. So this led to the very infamous ultraviolet catastrophe. And the problem was that if the wavelength which we were talking about and discussing were shifted more and more towards the UV region of the EM spectrum, the black body would start releasing an unbounded amount of energy. And it actually made no sense. If we are irradiating some finite amount of energy, it should also be emitting some finite amount of energy as well. And again, this uh, formula which was given by Rayleigh-Jean, this proved incomplete and was not the complete explanation to the black body problem. Now, a common thing which we have noticed until now is that we had been treating uh, light as waves until now. For example, even in the classical approach, we treated them as standing electromagnetic waves which were formed in the cavity of that particular black body. Now, next came Planck. And what he did was he completely turned the picture upside down, and he said that instead of considering a continuum of energy which is emitted in all wavelengths and all frequencies, let us quantize energy. So what Planck did is that he quantized electromagnetic radiation, and he said that energy could be emitted or absorbed in the form of EM waves only in certain discrete packets of energy. And these packets of energy came to be known as quanta. So the energy of a quanta could be given as h nu. So here nu is actually the frequency of or the frequency with which the energy is being emitted, and h is the Planck's constant which is introduced. And when he applied this relation to the partition function, he came up with his formula, which is given over here. And when this formula was compared with the experimental data, it was found that it matched pretty much well in all regions of the EM spectrum. So a thing to notice over here is that for as we increase the temperature, the peak of this curve, it starts, first of all, it starts rising, and secondly, it starts shifting leftwards. So as we increase the temperature, more and more energy is released in the region of shorter wavelengths. And you can see that this is what the classical theory proposed by Rayleigh and Jean was, and it diverged pretty much from what Planck had deduced. Okay, so this is a simulation on black body radiation, and you guys could scan this QR code from another device if you have, or I will be sharing the PPT as well. So from there also you can access this link. And just to show you guys, this is what the simulation actually looks like. Now, let's say if I keep the temperature of a body somewhat closer to a sun, so it would be emitting most of its light in the or the peak of its emission would be in the visible spectrum. And as I continue to lower down the temperature, the peak starts shifting rightwards. Now, an important thing to notice over here is that stars or objects which are at cooler temperature, or in general stars which are cooler than sun, they emit most of their light in the infrared region, whereas hotter objects, let's say stars like Sirius A is the brightest star which is visible in the night sky. So this emits most of its energy in the UV region of the EM spectrum. So this is something which we will be discussing again in one of the upcoming sections in today's session. And yeah, just remember this fact for a while. So coming back to this, so until now we have discussed what a black body is, how it works. Now the question is why? We have answered how, we have answered what. Now the question which we would be answering is why should we even care about introducing the concept of black bodies in astronomy or astrophysics? So as I had mentioned earlier, that stars, planets, dust clouds, these all celestial objects are actually a very good approximation of black body. So when we obtain the light curve data from them, we see that it matches pretty much closely to what a black body would have emitted at that particular temperature. And now that if we have got a model to describe black bodies, by using a similar model, we can apply it to celestial objects like stars. And using that, we can find several properties about them, be it their temperature, their radius, luminosity, the, the spectral distribution of energy which they are releasing, and what else. So, I mean, this is one of those few places in science where one single model, the model which Planck gave us to solve the black body problem, is used to describe certain phenomena, several phenomena in the universe, and that to great depth. So it is one of those interesting things. And yeah, that's what black body and black body radiation is all about. Now, the next topic which we would be discussing is how do we even study stars? Now we have got a model to relate stars to, but now the question is how do we study them? And we primarily use three methods or three techniques to study the stars in our neighborhood. So the first one is astrometry. So astrometry is basically the science where we are dealing with the position and the movement of stars. So we are calculating the distance from them, we are observing them, predicting their future position in the night sky. Next is photometry. So photometry is the part where we observe and measure the light which we are receiving from a star. So we study how much light we are receiving in particular section or particular band of the EM spectrum. Next, we have got spectroscopy. So, okay, so from photometry, we have received the light from the star, and in spectroscopy, we study and analyze the different light, which the different intensities of light which we have received throughout the entire band of light. And by doing so, we are able to calculate, let's say, the chemical composition of stars, or we are able to find the radial velocity and the rotational velocity of galaxies. So, astrometry is something which was earlier covered in modules related to celestial mechanics, coordinate system, etc. And photometry and spectroscopy is something which we would be discussing now in this session. So, let's start with photometry. Now, as I mentioned earlier, photometry is the science where we are observing a star and we are measuring the amount of light which we are receiving from it. So, what astronomers do is that they use instruments to gather light and then they apply something called band pass filters on them to isolate and segment light into certain wavelength ranges. So, it allows him to isolate light of certain region of the entire light curve data which they have received. So if you look over here, this is the Eta Carina stellar system, and this grayish or black shaded region which you see over here is the entire light curve data which we received from this stellar system. And when we apply several filters on it, we are able to isolate these colored patches. They are just for highlighting. So these colored patches of data from this entire data which we received from that particular star, we are able to isolate it and then study them separately to get to know much better about that particular star or celestial object. Okay, so coming to pass bands and photometric filters. Now, as I mentioned before, pass bands are certain regions or certain bands of frequency or wavelengths within the entire EM spectrum. And filters are the photometric filters are used to isolate the light which you have received from the stars and to isolate them and segment them into these particular pass bands. So let's say if you look at this data, now this blue curve which you can see over here is actually the light curve which we have received from a hot star. And this red curve which you can see is slightly shifted right is actually the light curve data which we have received from a cooler star. Now remember, as I had spoken earlier, that hotter stars emit much more in the UV range, whereas cooler stars emit much more in the red or the infrared region of the EM spectrum. So this is something which is quite evident over here in the data which we received as well. And these colored bands which you see in the bottom are actually the filters which we apply on this data to isolate certain sections of light, and these sections of light are then separately observed and studied. So some of the common filters which we use, first one being the UV rays. So the naming convention is quite easy. The first letter generally denotes the range or the region which we are observing. So U stands for ultraviolet, V for violet, R for red, I for infrared, and Z is denotion for near infrared region. GHK is also again used to observe in the near infrared region, and this is something which is used to study cooler objects or cooler stars in the night sky. So the next topic is of magnitude scale, which pertains to the brightness of object. And upcoming about after this, we will be discussing the topic of spectroscopy. So that is something which will be covered by Malay. So Malay, over to you.
So, hello guys, I am Malay. Uh, I am a volunteer in Kritika Club and I'll be presenting the rest of the presentation. So, as Pratham just said, luminosity and brightness are very important for studying any star or any object. So let's see what the luminosity looks like for normal objects. So consider the sun. So the solar luminosity is 3.8 into 10 to the 26 watts, if I remember correctly. So if I tell you that, okay, there's a star whose luminosity is 9 into 10 to the 27 watts, do you get any picture in your mind in which is brighter, sun or this star, or how much it is brighter? No, right? Because human minds are not built to imagine numbers on the scale 10 to the 26. So to simplify all these problems, we astronomers defined a magnitude scale which is used to measure the brightness of an object. So it is a reverse logarithmic scale. So it is defined so that if the difference in magnitudes is 5, then the star with the lower magnitude is exactly 100 times brighter than the other star. So you can see here that a magnitude 1 star has a relative brightness of 1, and a magnitude 3.5 becomes 0. 0.1. So note that lower magnitudes are more bright. So mathematically, you can express this as m2 minus m1 is minus 2.5 log b2 by b1. Uh, so astronomers use two types of magnitudes. One is the apparent magnitude. Apparent magnitude tells us what is the brightness of the star as we see it from the Earth. So if there's a very bright star which is very far, the flux from it would be distributed to the whole distance from the star to Earth, and hence what we'll see would be much less bright than, say, a less bright star which is much closer to Earth. So to capture this, we consider the flux observed, and the apparent magnitude is defined using that flux. So you can see that sun has an apparent magnitude of minus 27, and the brightest star in sky in night is minus 1.46. So a difference of almost minus 25 corresponds to uh, 100 to the power 5 difference in apparent flux. So it is a huge difference. So note that sun is around minus 20 to minus 30, moon is somewhere around minus 10, Venus is around minus 5, and the stars which the faintest stars which we have been able to detect are at plus 30. Naked eye can detect somewhere around plus 7, plus 8, depends on the viewing conditions. So just try to imagine the huge scale of fluxes we observe from Earth. So the next is an absolute magnitude. So to remove this distance factor, we have another scale. So uh, absolute magnitude essentially describes the intrinsic luminosity of the object. So you assume that the object, you calculate the apparent magnitude of the object, assuming it was placed at a standard distance from you. The distance is 10 parsecs from for stars, 1 AU for planets. So considering stars, so what is the magnitude of the star if it were closer to me? So say sun now, which was much brighter than Sirius, now has absolute magnitude of 4.83, while Sirius is at 1.4. It is brighter, it emits more light than the sun. So the faintest objects can be, for example, M87 galaxy, which is at minus 22, and there can be very bright objects which are ROS 25P, which is at 14.8. So from the inverse square law of light, we know that the observed brightness and the brightness, if we assume it is placed at 10, would uh, would depend on the square of the ratio of distances. From that, you can get the relation between apparent and absolute magnitude. So note that for apparent magnitude, you need a 0 point. So you need to agree that something should be 0, and that's arbitrary. Astronomers have chosen Vega to be the 0 point. So the apparent magnitude of Vega is fixed to be 0. So photometry. So we learned what photometry is. How do you measure light? So what do you learn from it? Why do you do it? So the first obvious thing you learn is how much light you are receiving. That tells you the apparent brightness of the object. Then if you know the luminosity of the object, say from some model, or if it's a standard candle, you can use the previous formula to find the distance of the object from Earth. So, for example, there are stars called RR Lyrae or Cepheid stars, which have a definite relationship between their time period and absolute magnitude. So, Cepheids and RR Lyrae are types of variable stars in which there is a pulsation. So, their core contracts and expands, due to which the light emitted by them follows a fixed pattern, an oscillatory pattern, which has a fixed time period, which has a relationship with its absolute magnitude. So, observing the time period tells us the absolute magnitude, from which we can calculate the distance of those stars from us. So, this is an important technique used in the distance ladder, about which you'll learn in the subsequent modules. Now, the other case is if you know the distance beforehand, so you can calculate distance via parallax or via other methods, then you can calculate the luminosity using the apparent magnitude. So, the next thing is temperature. So, we discussed that there are filters, there are pass bands. So, suppose you calculate the apparent magnitude in B filter and V filter. The difference of these magnitudes is called the color of the star. It's represented by a color index B minus V. And because the black body spectrum is a fixed function, you can calculate the temperature of the body from the difference in two bands. So the temperature and the luminosity together make a HR diagram. So an HR diagram is a diagram on which you plot the star against its absolute magnitude and color. So an HR diagram, when you collect all the observable stars and you plot them, you see that they're not randomly distributed as you would expect. Like, why would you expect the magnitude and temperature to be related? But they are actually related. So most stars fall on this line, which is the main sequence line, and there are some stars on other lines like supergiants, some are giants, white dwarfs. So essentially, from photometry, you can classify the star into what spectral category it is in. So one more thing is that if you know the luminosity and the temperature, by the direct formula, you get the radius of the star. So the next is variability. So photometry is the study of how much light you are getting in some particular wavelength region. Now consider that you put the sensor and you observe overnight how is this changing. So suppose your light was constant and then you observe a sudden dip in how much light was coming. Then it was constant, then you observed a smaller dip, so on. So from these time variability in the photometry, you can learn a lot about the stars. So there can be time variability due to the stars being variable. We already discussed about Cepheids and RR Lyrae. There could be eclipsing binaries. So basically two binary stars which are common revolving around their common center of mass. So when the one passes in front of the other, it blocks the light and hence you see a dip. While they are not blocking each other, the light is constant. So instead of two stars, it can also be a planet. So if one planet transits in front of a star, because of the planet, there is a very, very minute difference in brightness, which we can observe, thankfully. And this is a very important technique in detecting exoplanets. So, what else? So, extinction and reddening. So, when light from a star comes to us, it does not travel through vacuum. There are interstellar dust clouds everywhere in the universe from which this light passes. Now, this interstellar dust cloud obviously interacts with light. It has absorption, it scatters light, due to which it changes the profile of the light. So it shifts the color towards red, which due to which it is called reddening, and you can know the properties of this dust cloud from the light you gain. So yeah, so this is an example of a very huge dark cloud which is caused by nebula absorbing all the light coming from behind. So we move next to spectroscopy. So before starting, we'll watch this short video.
In 1835, French philosopher Auguste Comte wrote, "On the subject of stars, while we can conceive of the possibility of determining their shapes, their sizes, and their motions, we shall never be able by any means to study their chemical composition." Comte was assuming that acquiring this knowledge would require obtaining physical samples of the stars. But only 14 years later, the physicist Kirchhoff discovered that the chemical composition of a gas could be deduced from its light spectrum, viewed from any distance. If we shine a beam of white light through a glass prism, the light breaks up into the colors of the rainbow, which is called the visible spectrum. If a gas gets in the way of the light beam, it absorbs the light photons of very specific wavelengths, leaving its signature in the spectrum in the form of absorption lines. These absorption lines will vary, depending on the chemical nature of the intervening gas, enabling us to identify the chemical composition of far-off galaxies just by the light that comes from them.
So a short conclusion of this video would be that you should never ever in science say that no one will be able to achieve it, because 10 years later someone would come and disprove you. Uh, so yeah, let's move on. Uh, so what is spectroscopy? It is the study of the light received from the bodies with respect to different wavelengths. So photometry was just essentially studying the amount of light you're receiving. Spectroscopy splits that light into wavelengths and sees how the light varies with wavelength. So what is a spectrum? It is a plot of amount of radiation received versus the frequency or the wavelength. So you can see this is the spectrum of a sun, this is the spectrum of a light bulb. Essentially, anything which gives off light has a spectrum. So either that spectrum could look like this, you have light everywhere, or you could have lights in some sharp peaks, or you could have light everywhere except some points. So elaborating more, there are three types of spectrums: continuous spectrum, emission spectrum, and absorption spectrum. So a continuous spectrum is a spectrum in which somebody emits light over the whole frequency domain. An emission spectrum is something which emits at very particular wavelengths. So this makes sense because discrete energy is quantized in atoms. So if there is some hydrogen spectrum, suppose, you would expect it to be emission spectrum. You would not expect hydrogen to emit at all wavelengths. And the third is an absorption spectrum. It is essentially a continuous spectrum minus the emission spectrum. So it has huge dips at particular wavelength, but otherwise it's a continuous spectrum. So what can you detect from spectroscopy? So we saw that the spectrum of stars follows black body radiation, the black body curve. Well, that is an approximation. Stars are approximately black body emitters. So they have some emission patterns and absorption patterns on top of them. So suppose this is the spectrum observed by sun, the red part. You can clearly see that there are absorption lines which are very clear. So from these absorption lines, you can tell what elements are present in the star because each element has a unique absorption line. So note that even if there's a very tiny amount of the element present, that will have some effect on the spectrum which we can observe, and hence we can detect very trace elements. So this is the spectral line of hydrogen. Most of you would have seen it somewhere in chemistry, physics, somewhere. So yeah. So a fun fact: the uh, infrared spectroscopy done by James Webb Telescope is very very astonishing. We are capturing spectrums which we are using to study the surface and atmosphere of planets. We are studying the debris disk around stars and a lot of things. So from the spectrums, you can see that we found methane, ammonia, acetylene, hydrogen cyanide, carbon dioxide among the spectrums of different planets. And hence, James Webb Telescope is essentially being used to search for extraterrestrial life. So another fun fact, so in 19th century, when we were observing the spectrum of the sun, you were seeing a very thin green line, which you had never seen in any laboratory for hydrogen, helium, or any known element. So you were thinking that, okay, there is a new element in the sun which we have not seen anywhere. So they named it coronium. But it was later determined that that line was due to Fe13 plus. So Fe13 plus is so highly ionized that it is impossible to produce in laboratory, and hence you were unable to even think that that is possible. So yeah, let's move on. So what kind of spectrum matters to me? So suppose you have a continuous spectrum emitter. If you observe light from here, you'll see a continuous spectrum. Now suppose this light passes through a cloud of gas. So the gas will absorb some of the light wavelengths at which it can get excited, and it will emit them again when it comes back to the relaxed state. So if you observe from this angle, the cloud of gas, you'll see an emission spectrum, which is the emission spectrum of the gas. Now, when this light passes to the cloud of gas, if you see from here, you will see continuous spectrum, but the lights which are absorbed now have a lower intensity. This is an absorption spectrum. So based on from where you're observing what you're absorbing, you can see all three types of spectrum. So one clarification. So a star is an approximation of black body. It is not a black body. It does not emit a continuous spectrum. So essentially the core of a star that emits very, very closely to a black body radiation. But as that light moves outward, the outer layers of the star are much cooler and they show absorption features. And when the light leaves the star, it is an absorption spectrum. It has the properties of the absorption by the star layers. So yeah, is that all? We learned about what elements are present in spectroscopy over? Well, no. Now we'll welcome our dear friend, the Doppler effect. So, because of Doppler effect, an object which is moving towards us emits light which appears to be blue shifted, and an object moving away, the light from it appears to be red shifted. And this is very easily captured by the difference of wavelength being proportional to its speed. So, you can look at stars and you can tell the motion. So, you know the standard wavelength of, say, Balmer 2 line. So you observe where the Balmer 2 line is in the spectrum. From that, you can calculate the velocity of the star. So yeah, why do stellar objects move? Duh, bodies move. So one simple example is a star, a exoplanet rotating around a star. So if a exoplanet is revolving around the star is technically also revolving around its center of mass. This is a very small velocity, but a velocity nonetheless, and we can observe this. The Doppler effect due to this is captured by our uh, sensors, and this is a important method to detect exoplanets, and it is called radial velocity method. So another note that this is not the only method, so no only cause of the motion of stars. So even our sun, it is moving within Milky Way. So the objects have inherent velocities. That's normal, but that's not the whole story. So there is something called a cosmological redshift. So our universe is technically expanding, and the galaxies which are farther away from Earth are getting more farther away. And the Hubble's law states that the velocity with which these bodies are moving is proportional to the distance they are at from Earth. So, for far enough galaxies, we can say that this recessional velocity due to the expansion of the universe will be much larger than any peculiar velocity due to its actual motion. Uh, Sorry. And hence, from measuring the redshift, we get the velocity of these galaxies, and from that, we get the distance of these galaxies from us. So, we learn more of this in cosmology. So, there is something called 21 centimeter line of hydrogen. So, you might have heard about spins. So, when electron and protons have parallel spins in a neutral hydrogen atom, that is a slightly higher energy state than when they have anti-parallel spins. And this transition is a highly forbidden transition with a half-life of 11 million years, which is at a 21 centimeter. So 21 centimeter is in radio, so you can imagine how low energy transition this is. And yeah, so uh, the good thing about radio lines is that the atmosphere has no absorption for them. So the light directly reaches Earth and we can observe it from Earth. So using this 21 centimeter line, we have measured rotational velocities of galaxies. So the galaxy has a huge disk. So suppose the disk is rotating somehow. So the velocity of objects at the center would appear to be zero. The objects coming towards you would have an velocity omega r towards you, and going away would have a minus omega r. So from this, you can see a redshift on the disk of the galaxy. And we measured the velocity of the galaxy and we saw this curve. But it turns out that the observed curve was much higher than the expected curve. And this led to us hypothesizing that there is some dark matter, matter which does not interact with light, and hence we have never observed it, which is causing the gravitational forces, which is leading to this high velocity. So this 21 centimeter line is essentially very important in the study of galaxies and in saying that there is dark matter. Uh, so there is a third feature. So we saw that what line is there, how much it is shifted. The third feature is how broad is the line. So when you expect the light to have, when you expect hydrogen to have some absorption, you expect it to have the absorption at a very particular wavelength and not some wavelength plus one or minus one. So the lines in the absorption spectrum are supposed to be very thin, very distinct. But what happens is sometimes you observe broader lines. So this broadening is due to some physics phenomena, and that tells us a lot of information about the star itself. So, for example, there is some natural broadening, of course. So, the uncertainty principle tells us that delta E delta T is greater than equal to h prime by 2, which essentially tells that due to some uncertainty in us measuring time, there is uncertainty in the measurement of energy. This gives a natural broadening to the spectral lines. But there are other reasons. So, suppose a star is rotating. So, when the star has some rotation, the part which is coming towards you has a velocity omega r, and the part going away from you has a velocity minus omega r. So the particles here, when they emit light, the velocity, the light coming towards you will be both red shifted and blue shifted depending on where it is coming from, and that would give some breadth to the spectral line. Similarly, you could have other reasons. So, suppose the star is not rotating, but the particles in the star are very hot. So, these particles are moving at incredible velocities. So, this velocity can be in any random direction. So, this itself gives it some Doppler effect. So, this also leads to some broadening of light. So there can be other reasons like some pressure or some magnetic field, which also cause broadening of spectral lengths. So let's come to the last topic. So we have talked about uh, photometry, spectroscopy. These were kind of measuring the intensity of light. Light has one more property, which is polarization, which can also give us significant information about the celestial objects. So polarimetry is simply study of orientation and the degree of polarization of light coming to us. So from that we get some information on the magnetic field of the emitter, the galaxy, the jet, whatever it is. We get information about the scattering geometry of dust clouds or disks. We know about surface properties of planets, etc., and some asymmetries in supernovae or stellar winds. So these are some situations in which polarized light is caused in astronomy. So look at this planet. It is receiving a lot of light. But when this light is scattered from the surface of the planet, this is polarized in one direction. So Rayleigh scattering polarizes light. Similarly, when dust scatters light in some debris disk, that also polarizes light. So if there's a very strong magnetic field, that produces synchrotron radiation, which is highly polarized. Similarly, magnetic field splits spectral lines into polarized components, and this is called Zeeman splitting. And from that, you can infer the magnetic field strength and the direction. So, see, this is a protoplanetary disk which is observed in the total light. And when you observe it under a polarized light, the light is much sharper. So, from these features, you can learn a lot about celestial bodies. So, thank you. Hope you learned something. Hope you had fun. If you have any questions, feel free to ask.